Morning, everybody, or afternoon or evening, wherever it is, whatever it is, wherever you are. Couple of updates for today. I realized that as I was moving along through uploading the video yesterday, I didn't publish it until this morning. I didn't realize I didn't hit the publish, like make available button. So you're probably seeing yesterday's at a time much later than normal. So I'm gonna assume that since I announced the quiz yesterday and I just made that video available, so I'm gonna go ahead and say that there's not gonna be a quiz today because probably lots of you haven't watched the video, and so we're just gonna forget that and stick with the homework quizzes and go with that. But that notwithstanding, we do still have PLC 7 this week for Friday. Usual PLC format with the quiz style, and then homework 4 is slated for Tuesday next week. And so at that point, we will add a quiz on homework stuff. So that's what's upcoming. And I think since we have dealt with single mirrors, we are now going to move into single lenses and the refraction of light from one medium into another medium. So we'll start with the refraction, we'll do some Snell's law examples, and then we'll go back into lenses, which are going to, with a couple of assumptions, they're going to obey the same types of, or they're going to be described, I should say, by the same type of things as the mirrors were, plus a few other little optional extras that we're going to throw in on there. So that's what we have going on today, or in the next couple of days, this week and next. And we're going to move on to refraction. So let's start talking a little bit about refraction. Now, I described refraction last week as a consequence of Fermat's principle and the least time principle, saying that the least time, or really, as we know it, it's the extremum time, and ultimately it's a lot of different things, but nonetheless, we'll start with least time. The idea of the least time comes about with refraction because there is a speed difference between two media. Okay, so one of the things that we want to talk about is that light travels, and we're still in geometric optics, by the way, so light is still traveling in a straight line, but light travels at different speeds in different, what's called media. So if I think of air, and I think of vacuum, and I think of water, and I think of glass, and I think of other things like that, we find that we have different speeds of light within those materials. And the quantification of this speed lowering is given by a quantity known as the index of refraction, which I introduced as part of Snell's law. So this gives rise to what's called the index of refraction. It leads us to define a quantity which helps us quantify how much is the speed of light different from its vacuum value. Okay, the index of refraction is going to be known as n. And essentially what it is the ratio of speed of light in vacuum to speed of light in material. So we have light speed in vacuum divided by light speed in material. We have the ability to then say that since light speed in a vacuum is the fastest possible thing for information to travel from one place to another, it's not the fastest possible thing, it's just the fastest possible way to get information from one place to another. Since every other material will have a light speed less than the speed of light in a vacuum, therefore we expect the index to be 1 if you're in a vacuum, or greater than 1 because the denominator is smaller than the numerator. Okay, the speed of light in a vacuum is a fairly well-known number. We call it c. And that, given this class, that is not the heat capacity or the specific heat capacity. That is the speed of light. And it is from the Latin word celeritas, which means really, really frickin' fast. So for us, we'll say that the light speed is 3 times 10 to the 8 meters per second. If you like standard or what are called standard units, which are now not standard for anyone, because those are the standard units, you could say it's approximately 186,000 miles per second. Which means it gets to the moon. Moon's about 250,000 miles away. So it gets to the moon in a little over 1 second, and it bounces off the moon. We have a mirror up there to tell us how far away the moon is by assuming light travel time. So it gets there and back in about 2.5-ish seconds or so. So that's pretty fast. You could also switch to kilometers, it'd be 300,000 kilometers per second. It's fairly quick. And also another really interesting one is if you go down further, it's about 30 centimeters per nanosecond. And 30 centimeters is about a foot. So light travels about 1 foot per nanosecond. And that basically helps to define the size of the computer that you're using, because if the processor is able to do so many calculations per second, then the information has to be close by, because it can only travel basically as fast as that. Okay, and even slightly less in the wires and stuff in the computer, but nonetheless, as processor speeds go up, the sizes of the computers must be going down, because it's the situation where the size of the computer and the memory is physically restraining how many calculations per second that the thing can do, right? So if you have, like it was when I was growing up, you have computers which are barely fitting in a room, that means that the information is way over there, and we have to go get it, and it has to come all the way back over here, and then we do a calculation, and then we go get that information that's way over there, and we bring it way over here, and the processor is very slow, because it's just waiting around for information to show up. Now that we have these small little things, right? We have these small little things, the processor speed, they can do billions of calculations a second, because the information is less than 12 inches away, right? So they can do these. They can get the information as quickly as possible. Anyway, a little bit of a thing on light speed there. Light speed in a material typically less than this, so we would call this something like c divided by v, v in the material. Okay. Now, because you haven't been required to take 4B prior to this class, we can't go into too much on where the physical origins of the index of refraction comes from. But if you have had 4B, this is a material property, and it's very related to the polarizability of a material and its dielectric constant. So if you have had 4B and you've talked about the propagation of electric fields in a material, well, that's essentially what we're doing. This is what light is. It's propagation of an electromagnetic wave in a material, and therefore is the behavior of the material is described by things like its atomic polarizability and its dielectric constant, and those lead to the index of refraction. So it's all kind of related, but we can't go into that because that's not a requirement. So what we're going to do is we're going to look at Snell's law here. which involves the index in the material in which light is arriving and the index in which the material is leaving. So Snell's law, right, which as we know is a consequence of Fermat's principle. It tells us that for an incident light ray, the index in that material times the incoming angle is going to equal the same exact quantity for the refracted material, the refracted ray, right? Material in which light is incident and the material in which light is refracted. Let me give you a drawing to go along with this. Looks like we can do that over here. If I have, for example, a situation here where I have something like air, this would be N1, and glass, we'll say, is N2. Now, how can I write N1 and N2? I don't know yet. Well, I'm planning on having the light incident from the air, so that if I draw this as my light ray incoming, that means that this is the incident side, and this will be the refracted side. And the angle that I'm going to measure on the incident side would be measured from the normal. We're going to drop a normal to the place where the where the incident ray is meeting the material. Okay, so that means this right here. And I'm going to go all the way down through here. That right there is my normal. And if you recall our mirror discussion, we always measure angles from the normal rather than to the surface here. We're going to be measuring this angle right in here. This is our theta 1 in the way that I am drawing this one. All right. Our incident side has an index here and an angle here. The refracted side, as it turns out, we can make a guess as to what the refracted ray is going to look like. And this is, by the way, this is the simplest possible case, a single ray, which doesn't exist in nature, but that's okay. We're just looking at it here. We're thinking about it. Here I have glass and glass is N2. You wonder, is the glass index going to be greater than the air index? Well, yes, because in glass, the light speed is going to be much lower than the light speed in air. The light speed in air is really similar to the light speed in vacuum. Therefore, the index of air is usually written as 1, even though it's not a vacuum, right? So for this situation here, for air, we are generally going to use 1, and that's not a bad approximation because it only changes in about the 3rd or 4th decimal point, if I'm remembering. So it's 1.0002, which is close enough for our purposes to 1. So we'll do this. Glass is usually around 1.5, which, if you look at what that means, right? What that means is I'm ending up with an index of 1.5. If I have an index of 1.5, that means that I'm basically taking 2/3 down here and then flipping it over. If I say that this is 1 and that's 2/3, that tells you that inside glass, light is actually traveling about 1/3 slower than normal. It's so slow in glass that it's only traveling about 67% of its normal speed. And hopefully that kind of makes sense because of glass being a slightly more dense and more refractory in material than, say, air. Air is not really going to do much to affect the speed of light. So here for glass, we're going to say this is going to be a bigger quantity. This N2 is a larger quantity. So if I were to think about the quantity of n1 times sine theta 1, and I'm going to increase n, what do you suppose that means I'm going to have to do to sine theta 2? Well, that's going to have to decrease. And if you think about the sine for angles less than 90 is kind of linear. In other words, if I think about what the sine looks like, if I graph sine of theta, right? Sine of theta is going to go like this up to about pi over 2, or I should say 90 degrees because we're using degrees. Sorry about that. 90 degrees. So if we're looking at angles that are back in here, the increase is essentially linear. Okay. Therefore, if I decrease sine theta 2, I'm decreasing theta 2. And that means that when I look at how I'm going to measure a theta 2 that's going to be less than theta 1, if I continue this line down here, it would look approximately like that. And that means that I'm going to have an angle which is less than that in the glass medium. So I'll just draw one that's there, and I'll call this theta 2. Like so. You will find that this is typical for materials in which the index has increased, right? If the index increases, the angle decreases, and therefore the light is bent towards the normal, if that makes sense, right? Because here's the normal, and it was going to be over here if there was no difference, but now it's way over here. So I usually typically think of that as it bends it towards the normal, or it bends it kind of, it shallows the angle down, something like that. Now, since we know that light's path is reversible, we could equally have said, what happens if the light starts in the glass and goes to the air? And you'd say, well, I could just do all of this over again. True. I could reverse this path and find that the light comes up and goes out along that exact path. And I wouldn't really have any problems just saying, oh, well, why can't this be N2 and this be N1? Well, it's useful to make sure that you're always calling where the light starts, number 1, and where it ends, number 2. And just getting into that habit really helps because, like I said, this is the simplest possible situation. I'm not going to give you the simplest possible situation to work on because we're already discussing it now. And so when you have to think about light going through multiple layers of things, you got to keep track of it. And you're going to start at 1 and go to 2, and then you're going to make number 2 equal to number 1 and keep going, right? So you have to chase the light through several boundaries. So if light comes up and goes out, you're going to notice that it bends away from the normal, right? And it kind of widens this angle out, okay? So if it was glass to air, we would do basically the same thing, but we would draw the light ray as going further out with a larger theta in the refracted sense. Okay, so with this now, what we can do is take a look at a couple of examples just to see what happens when we try to apply some of this. And it's usually fairly straightforward in its application. Okay, so what I want to do is show you, I'm going to just see if I can show you some refraction through a piece of acrylic here, which I brought in. So let's move you down to the desk here and see if this will show up. I'm going to take this, let's move you down here. All right, so that you can see the, let's move this back a little bit. And I think I'm going to have to shut the lights off so that you can have a chance of seeing the light ray that I'm about to put on here. All right, so what I have here is a light box with just a single slit in it. So it's approximating a light ray. And I have a piece of acrylic here, which is shaped like a ramp. And I'm just going to put that down. And if we shine light straight through it, you can hopefully kind of see, if you can kind of see it on the paper moving here, right, as it moves around. I'm going to go turn the overhead lights off so you can see it like that, so that we can see the light ray on the paper. Hopefully it will show up. Ah, good. Oh, that looks good. Okay, I'm pleased with this. Maybe what I'd like to even do is have it tilted a little bit more. So let's just pop that underneath here. Okay. Okay. So what I have here right now is a completely trivial situation in which the light is entering straight along the normal. In other words, it is oriented 0 degrees away from the normal and 90 degrees away from the surface. And therefore, if you think about the sign of 0, well, it doesn't do anything, right? It keeps going along and along. Now, hopefully, this gets to be kind of an interesting situation when I start to change the angle. So I'm going to just rotate this rather than move the light source. And now you can see, I think, that I'm getting some displacement in the beam. Here's the path. The normal is now pointed somewhere like here. And what's happening is I'm getting refraction within the block of plastic here, and then refraction again when the light exits the block of plastic or acrylic or whatever this stuff is, and continues on its merry way. You notice, however, that it's displaced from its original path, right? It's still parallel, right? The beam's parallel to the original beam. The ending beam is parallel to the original beam, but it's now displaced by a certain amount of distance, which we could probably figure out. And the more I turn this, right, the more it's going to displace. Alrighty, so what we have then is that situation there. And now if I can, you can't really see it too well inside the material. I can try to do this to show you, but I don't think this is going to work super well because it has to be, even just looking straight down into the material, you can't really see the actual light. So all you can infer is that the light traveled in the material from here over to there, and then we'd have to measure those angles. All right. One other interesting thing here is perhaps you can see these rays that are coming out over here, and that is due to reflection off the top surface here. And then there's another ray that's coming out right there. I'm not sure if you can see that one. It's pretty faint, but that's due to reflection off the bottom surface and then refraction out of this side right here. So that's what refraction is like. It's yeah, you can't really see it if I turn, but it's just the moving. It's the not displacement. It's the changing of direction of the beam due to differences in the speed. Okay, so that is the situation of refraction here. And so now I gotta walk a country mile and go turn the lights back on. Hopefully you can see most of what I have. Oh, we got to erase that. Okay, good. Okay. So let's take a look at an example, or a couple of examples of light which is going from one medium to another. We'll start with something fairly straightforward. just a fairly straightforward application of Snell's law at a single boundary, and then we'll move to one with multiple boundaries. All right, so let's suppose that I have a boundary here and an N1 and an N2. And I'm going to have light impinge from the left onto this surface at some angle, and I'm going to wonder what's the refracted ray angle here. So here. Well, actually, let's do this first. Let's come up with this situation first. So here's a ray coming in, about like that. Okay, so here's a ray coming in. This is N1. This is, of course, my incident side here. If I'm going to drop a normal here, like so, then I can measure this angle. This is theta 1, right here. And so the first question we could say here is, suppose that I know the index N1. Say it's something like 1.7. And I have light incident on this boundary at an angle of like 30 degrees. If I then measure the refracted angle out here, and I look and see what's the angle in theta 2, what's the angle theta 2 over here in N2, and suppose that angle was 30 degrees. What if theta 1 was equal to theta 2? Well, if theta 1 was equal to theta 2, what that means is the light has basically continued traveling exactly in the same path that it was traveling, and therefore there was no change in the speed, and therefore there was no change in the index. Therefore, if that was 30 degrees and that was 30 degrees, then this index is equal to this index. So let's just suppose that we can figure out at what angle, right, did I shine light in here such that it was refracted at the exact same angle. Then I can tell you, oh, I know what these two are. Okay. All right, that's the trivial case. Let's suppose now, I'm just going to leave this line in here as a reference. It's dashed now, so that's the path of the light. Suppose now that N2 is larger, it's 2.4, and N1, let's say, is 1.7. Let's say N1 is 1.7 and N2 is 2.4. 2.4, incidentally, is a nice number to have because it is close to the index of one of the highest naturally occurring index materials, which is diamond, in fact. Naturally occurring material, diamond. And so the people who mine diamonds and polish them up and cut them and make them all beautiful for people to have as jewelry are relying on this high index because of how light refracts and from air into diamond, and then consequently also on the way out, what happens to the light on the way from the diamond out into the air, and it gives it this sparkling quality. And the sparkling quality of the diamond is something that the diamond industry really relies on, and it promotes as the thing that, you know it's a diamond because it sparkles, and nothing sparkles like a diamond. And that's basically down to the high index of refraction that it has. However, of course, we have the ability to synthesize materials that have index of refraction that is similar to diamond or even higher. And so if you wanted a very sparkly material, one which had an even higher index than diamond, you could get this. And if you are in the market for a wedding ring or something like that, then you could save yourself a lot of money by getting a material whose index is higher than this, and it therefore sparkles even more
And people like it a lot more, but then the diamond industry has to poo-poo it because they have to say, well, that's too sparkly. That doesn't sparkle like a diamond sparkles. That's too much. You have the correct thing. If you're interested in this material, it is called cubic zirconia, and you have probably heard of it, but it sparkles more than diamond, and it was created such that it had a higher index of refraction than diamond. Anyways, nonetheless, that story notwithstanding. If we go 1.7 to 2.4, that's the same situation as going air into glass. I'm increasing the index. Okay? So when I look at my Snell's mathematical representation here, if n1 is lower and n2 is bigger, then I know that this angle of theta 2 has to be lower than the theta 1, which means I should be able to draw this as bending towards the normal this way, like that, and therefore this angle here would be theta 2. Okay? So let's suppose that we have an angle of incidence. Suppose our theta 1 is something like 60 degrees, and let's figure out what theta 2 is going to be. So we're going to say I'm interested in solving for the sine of theta 2, so that's going to be the index ratio multiplied by the sine of theta 1. And therefore, when I look at this, and then I usually will stop with the solving right there, and I won't write out the algebraic or the inverse trig function, say inverse sine of such and such. I don't usually bother to do that. The sine of theta 2, therefore, is n1 over n2, which is 1.7 over 2.4. And suppose we say that's 60 degrees. The sine of 60 degrees, you may know it should be 0.866. And therefore, you're going to see you're going to reduce that number, right? And so if I reduce the sine, like I was telling you before here, if I reduce the sine, I reduce the angle. And therefore, this sine is going to be the sine of this angle is going to be some number here, and therefore, theta 2 we can figure out as being some number here, which is less than 60 degrees. Okay, and let's see here. I got about 38 degrees when I did that. Alrighty. Alright, so that's an application of Snell's law at a boundary. Let's take a look at another situation where now we have multiple boundaries. And actually, pursuant to that. Suppose that, I'm going to use this example for just another thing here. Suppose that I have a block of this 2.4 index stuff, like I just had the block of acrylic. The block of acrylic has an index, but it was surrounded by air, which had a smaller index. So suppose we have the same situation here. Suppose that I have a boundary here of the 2.4 stuff, and then out here it's going to go back to 1.7 again. So suppose this is N1 again, 1.7. I'm going to call it N3 though, because this is the third material in line. But suppose that N3 is equal to N1. What happens to the path of the light? Well, you're going to say, well, I gotta get Snell's law here, and I'm going to draw my normal, and then I'm going to know that it's going from an higher index to a lower index, so that means it has to bend away from the normal, and once it comes here, it's going to bend away from the normal, and it's going to go something like this, and this would be theta 3, like that. Now, if N3 is equal to N1, what do you suppose sine theta 3 is equal to? Maybe you could see it's going to be equal to the sine of theta 1. And this is what I call chaining. And I don't think that's a term in widespread use, but I'm chaining the use of Snell's law. So take a look. If I take Snell's law and I apply it at the boundary here, I would write that n1 times sine theta 1 is equal to n2 times sine theta 2. And then, as long as these boundaries are parallel, what I would then write is, since theta 2 is that one, then theta 2 is also this one. Theta 2 is the outgoing angle here, but that's also the incident angle here because these surfaces are parallel. Now, if I had a different surface here, I couldn't say that, right? I'd have to draw the normal and then figure out the new theta 3. I'm sorry, the new incoming angle to this. I don't know what you call it. Okay, so because these boundaries are parallel, I can say that the outgoing angle here is the same as the incoming angle here, and therefore n2 sine theta 2 is here, and that's going to equal n3 sine theta 3. So I don't need to calculate anything to do with sine theta 2 if all I'm interested in is what happens to theta 3. Because all I can do is say, well, it was coming in at this angle and it's leaving at this angle, and that's exactly what you were seeing when you saw the light go into the material, refract, and then come out of the acrylic. But it's exactly along the same path, just displaced, right? And that's exactly what you're seeing here. Here's the original line of the light, and it's displaced by a certain amount right here. Okay, so as long as you have parallel boundaries, then you can say the outgoing angle from this refraction is going to be equal to the incoming angle at this refraction here. All right. So that's a little bit of news on that one. Now, suppose that we have a situation in which the boundaries are not they're not parallel to each other. Okay, so let's do another one here, where we have to think about what our angle is, right? Like I said, if this boundary wasn't parallel to this one, then I can't say that the theta incoming here is the same as the theta outgoing there. So let's do another one and say that, let's say here that I've got a boundary here and a boundary here. All right, so I've got an N1 there, an N2 here in all of this stuff, and then my N3 out there. All right. Let's suppose that we have, whoa. Let's suppose that we have a dry throat. Let's suppose that we have light incident here, like that, and it goes in and comes out like that. I'm not going to draw what happens after this point because we're going to look at that in a minute, but I'm going to drop a normal here. All right, and I'm going to look and see what, so first off, let's suppose that we measure this angle. I'm going to call this angle, say, phi. All right, now it's something to watch out for. This is a very, I don't know if this is a very simple thing or a very, it's not a super common thing, but it's one of those things where it's just like, well, I measured this angle. Okay. Well, now I can't use that angle straight as it sits. I have to go find out what this angle is, right? So it's just one of those things where it's the recognition that just because I have an angle doesn't mean I can just pop it straight into Snell's law. All right. So let's assume that we know these two indices. Think for a minute, if I tell you again that N1 is 1.7. If I tell you that N1 is 1.7, excuse me, relative to 1.7, what is N2? Is it 1.7? Is it less than 1.7? Is it more than 1.7? What is N2 relative to N1? Okay. Now look at the path of the light and maybe compare it to what was happening over here. Okay, so the light here is coming in at this angle and bending in towards the normal. This light here is coming in towards there at this angle, but it's bending away from the normal. Okay, so that to me says that N2 is less than N1 because this angle, and when I say this angle, it's not this one. It would have to be this one. Right? This one here, which is 90 minus phi, is larger than theta 1. And therefore, I would be able to say that the speed of light here is faster in N2 than in N1. No, it's faster in N2 than it is in N1. So here, let's suppose that this is a lower index. So let's suppose that it's 1.6 or something. Okay. And this thing here is our theta 2. Let's say here's theta 2. I'm going to have to erase a bunch of this stuff as we kind of go on to the next part of this and we talk about what's going to happen at this boundary over here. But right now we're only concentrating on this refraction right here. Okay. The angle is theta 1. Suppose we measure the angle phi and we know the angle phi to be something like 60 degrees. Then we would know that theta 2 is 30 degrees. And like I said before, that measurement of that angle is really only in there to make sure you know you don't want this angle, you want this angle. Okay? So it's just one of those things where it's just keep an eye on that to make sure that we're getting the right angles in place here. All right, let's suppose we're going to try and find theta 1 here. We'll apply Snell's law at this refraction at the boundary here. Okay, so I've got my theta 1 in the N1 material, I've got my theta 2 in the N2 material, and therefore theta 1. Okay, this is a little bit the opposite of what we were doing over there, where we were looking for the refracted angle. Now I measured an angle, and therefore was able to figure out what the refracted angle was. Now I'm looking for the incident angle. Okay, so now it's N2 over N1, ratio of indices times sine theta 2. And this is 30 degrees, and N2 is 1.6, and N1 is 1.7. And sine of 30 degrees, you know is, or you probably know, is a half. So we're going to calculate this whole number and then we can figure out what theta 2 is. Theta 2. We can figure out what theta 1 is, the incident angle. Alright, and let's see, I think I calculated that and I got something like 28 degrees. Okay, now does that make sense? Just give it a quick eyeball, always a useful thing to do. And one of the things you can think about is, if I reverse the path of light and I shine light this way, would I expect this behavior, this angle, to be lowered? Yeah, I would, right? Because I'm going to a bigger index if light's going that way, opposite to what I have in the problem. In exactly the way that we just did over here, right? It bends towards the normal in a bigger index, and so here it's bending towards the normal in a bigger index, so this angle should be less than that angle, and so that kind of is all right. And then you just kind of expand your thinking to say, well, it's got to be less because it widened out over here and went to a material of lower index, right? So it's going to lower index, meaning higher speed, and therefore that's a larger angle. that one is a larger angle than that. All right. Okay, so that takes care of the first part, but now let's get on to the next piece, which is dealing with this boundary right here. I'm going to erase a little bit of this so that I can use a little bit of that right here. And I want to show you a phenomenon. I'd like to show you a phenomenon. Sorry, but this is going to involve me running all the way down to Lower Campus to turn the lights off in this room again, and then running all the way back. Feels like I'm running to Thailand, but it's not that far, I guess. So I'm going to move you down here again. Alrighty, so hang on to your seatbelts. We're going to go down here again. And we see this. Alright, so we're here again. Let's turn this thing on. Alrighty, so now we're going to do this. Now I want to show you something a little kind of, let's turn it this way. Kind of interesting here. Alright, let's see. Alright, so let me go get the lights. Okay. Alright, so now what do we have? Well, I just turned it 90 degrees so you can see it. This is the displaced beam. It's a little bit further away than, or it's not on the same path as this one. What I want to do, and here you can see a little bit better the reflections. So here's the incident beam and it's reflected there. And here inside the block of plastic, here is where the light hits the second surface down here, which you can't really see too well, but maybe now you can when I put a little bit of contrast there. Then you can see that this beam comes out, where is it? Right there. You can see that beam that's just coming out right there is due to a reflection from that lower surface. Now what I'd like to do is, what I'd like to do is have it come in. I want to move it so it's over here. Okay. And about there. Okay. So what I have now is I have the light coming in. I'm going to scoot this forwards here. Okay, I have the light coming into the slanted surface here, and I'm looking at this beam that's getting refracted out here. So light's refracting inside the small little triangular piece right here. But notice what is happening as I turn this back so that the normal is, well, that's not the normal, but as I turn it back so that it's a little bit more normally incident, right? Watch what happens to this refracted beam. As I turn it this way, right? As I turn it this way, and I don't know if you can quite see this, but I'm getting a really good rainbow effect right here. I can definitely see red and blue on either side of this line. And I'm not sure, I'm looking at the screen and I'm not sure if you can. But as I turn this thing this way, and I turn it, 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 where'd the beam go? No beam. Here it is, and there it goes. So what the heck's going on here, right? I can make the same type of thing happen here, where I'm getting the material here, and I'm with my same displaced angle, same displaced rays here, right? My displaced ray, and I start to turn it, and you can see that I'm getting more and more, more and more, more and more, and now all of a sudden, it's coming out over here. It's not coming out over here anymore. That's weird, isn't it? I find that kind of strange. Well, there we go. Here it is. Right, there's my displaced beam. Right? The incoming beam is a way over here, and now it's refracted out here. But what I have going here is as I turn it and turn it and turn it,
all of a sudden this thing appears. And it's not exiting the material over here anymore. That's a pretty big change going from a kind of a straight path there to this path over here, right? So, what's going on when we do that? And you can think, right, it's the same thing over here, right? Here it is as it comes in. This is the path after it's refracted out of the material. And as I turn it and 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 turn it, boop, now it becomes this one. And you could kind of see that one. They're both kind of here, right? They're both here. Boy, that's a good rainbow I got on this one. I don't know if you can see that. Anyways, what is going on? What's happening is the light is no longer refracting out from this surface over here. This is the slanted surface. That's where it was exiting. It's exiting right here on the slanted surface. And now as I turn it this way, it's no longer able to do that. So we have to come up with a description to this. This is a situation where my refracted beam, okay, if I look at the normal to this surface, the normal to this surface is here, but as I slide the ray closer and closer and closer, that refracted beam here is getting closer and closer to 90 degrees. And pretty soon it's gone. So right there, let's see if I can find exactly where it disappears. So there it is there, and now it's gone. So this right here is a situation where the refracted ray is refracted so much by the air, right? It's going from a material of it's going from a material of higher index to lower index, right? Acrylic to air, but it's getting refracted so much that the refracted ray is coming out at an angle of 90 degrees or something like that. All right, so how do we deal with this? It's so big that the angle is actually not allowing the light to leave the material. Okay, so imagine what happens here if I draw the same type of thing. Okay, let's do this. All right, I'm gonna go run and get the lights back on, and then we'll roll. Okay, wow, that's a long walk. Suppose that we have the material oriented such that the exact same thing that I just showed you is now happening at this boundary. In other words, the light is not leaving material N2, it's bouncing off and going this way. Okay, what this means is, here's my normal to that surface at that point. What that means is, if I had the ability to independently rotate this boundary slightly with respect to this one, right? There was a time when I could have the boundary such that this refracted ray came out like this, right? And then came out like this, and then came out like this, and then came like that, and eventually I turned it to this point, and the refraction into N3 is now gone. That's what I was trying to show you with the plastic block. The refraction into air from that surface is gone. And it is completely reflected off that surface within the material. And since it is reflected, we call it a reflection. And since it's completely within the material, we call it completely internal reflection or total internal reflection. Okay, so that's what's happening at a boundary like this, where there is no refraction any longer, it's reflected. Okay, this is the situation of total internal reflection. Because what's happened is theta 2 has gone to 90 degrees. The refracted ray has gone to 90 degrees. Okay, that's what I mean when I draw these refracted rays, that I turn the material and I turn the material and I turn it and I turn it and I turn it, and the refracted ray goes, and then it's gone. And so, because the light still has to be there, it just doesn't leave, it reflects instead. So what we say is that if you have the material right at the point where the refracted ray has just disappeared, okay? In other words, theta 2 is now essentially 90 degrees. Here's how we mathematically model that, because we can't have the, well, we'll look at it mathematically in a minute, but it's not going to be possible for that angle to be more than 90. And I'll show you why. Mathematically, it doesn't like it. But the idea is that if theta 2 is equal to 90 degrees, then what we say is theta 1 is a critical angle. That's the angle at which you have extinguished all of the refraction and you have switched to total internal reflection. Okay, we call that the critical angle. And that's the angle of incidence at which reflection happens. Okay, so let's take a look at this mathematically. And I want to apply it to this refraction right here. Or reflection right here, as you might say. We don't need this anymore, so let's get rid of that. Okay, so I'm going to look at that point right there, and I'm going to say, okay, let's look at n1 sine theta 1 and n2 sine theta 2. Okay, now I'm going to call n1, right? Now I have to think of my n1 as being the incident stuff. Right? This is all incident. So now I'm going to look at the incident ray as coming from the N2 material. So this is N2. I'm going to call this now right here. Right? I can't call that theta 2 anymore because I called that theta 2. So let's call that theta I. Okay? Let's call that theta I. Sine of theta I. And that's going to be N3 times the sine of the angle out here, but the angle out here of the refracted ray, okay, of the refracted ray. Remember how I showed you there were two beams? There's one that's refracted and one that's reflected. What we've done is we've extinguished the refracted one because we've moved it to 90 degrees. So we put in 90 degrees for the refracted angle, because what we're assuming is the refracted ray is coming out like this and basically not leaving. So it's as if you can think of the light that's leaving as a sum of two parts, the refracted ray and the reflected ray. Okay? Because off every surface there's usually a reflection. It's just that now the reflection is dominating because the refraction isn't able to leave the material. Okay? So we say that at 90 degrees, that's when it's all completely internally reflected. The question is, what's this angle? Because then we'd be able to find out what N3 is. And I remember I didn't tell you what N3 was. So let's try and solve for N3. Okay, so we're going to have to find out what theta I is in order to do that. Sine of 90 degrees is just equal to 1. So I don't have to do any rearranging algebraically here. It's already kind of sitting here for me to solve for N3. Sine theta I is that one right there. This one here. And so what do we have? We have a triangle. We have a triangle here. Like that. And so I know what this angle is. And I know what this angle is, right? So this angle, theta I, has to be the same as phi because they're parallel angles. Right? This one here is the same as that one there. So theta I is equal to phi, and that's 60 degrees. Therefore, N3 is going to be N2 times the sine of 60 degrees, and that's N2 is 1.6 times the sine of 60 degrees. Okay, this is going to be a number less than N2. Does that make sense? I hope so, because there's no way that you can have a higher index material out here and have this ray bending further and further and further away from the normal. You have to be going to a material of lower index in order to make this behavior happen. Otherwise, it's going to blow up. It's not going to work for you. Okay. Let's see. If you calculate this, that's like 0.8 of this, so it's about 1.4.
Say, all right. We have a 1.7, a 1.6, and a 1.4. Okay, so we figured that out. But notice that this behavior is dependent on going to a lower index. If we go to a higher index, the bending is towards the normal. That means this line here, that means the ray would have been out here, and there's no way I can get this total internal reflection because I can't get the refracted ray close to 90 degrees. It's going to be getting closer and closer to 0 degrees. All right. Okay. Incidentally, total internal reflection is a very useful thing and also a very wonderful thing. And I'll give you an example. We use fiber optic, well, we used to. I don't know if I guess we still kind of do. I don't know if we've grown out of it yet, but the fiber optic cable is designed such that the angle of incident is usually always less than the critical angle. Wait, wrong way to say that. The angle of incidence is less than the critical angle. No, yeah, that's right. The critical angle is always greater. No, wait a sec. Hold on, I'm getting myself confused here. If I wanted this to come out, then it would have had to have gone to there. So the incident angles are always greater than the critical angles in a fiber optic cable. Thank you. The critical angle is such that no matter almost within a range of what incident angle you shoot it at, it will bounce in and out of the fiber optic, not in and out, but up and down within the cable for thousands of miles before it emerges on the other end. What that means is there's very little signal loss, and it's been worked on for decades to get a fiber optic index that's just good enough to basically have almost no loss as the signal travels, for example, across the Atlantic. I mean, we laid fiber optic cable on the bottom of the Atlantic Ocean, and that's how before we had satellite communications, that's how people in the United States could call people in the European or the continent over there, because you could get a fiber optic signal underneath the ocean and it would travel, and it would be great. You would have basically no loss of signal. You'd be like the person sitting almost in the room with you, right? So that's one thing. But also, more importantly, total internal reflection is essential for rainbows to happen. How does that work? Well, I'll sketch it out really quickly here for you, but we do have to move on to lenses. Essentially, you think about a raindrop, okay? A droplet of water suspended in the air, and you think about the sunlight that's coming to hit it. Now, if the sunlight's coming to hit it like this, right, and in comes the sunlight, well, here's a normal, and this is water, so it's going to refract towards the normal, like that. But then it's going to get over here, and as it tries to exit, no, the normal's more like this. As it tries to exit, it's going to find that the critical angle, it might be incident near the critical angle, or more than the critical angle. So if it's incident more than the critical angle, I get reflection here, and this bounces like that, and then refracts out. And how would I have it refracting out of here? Looks like it's coming about like that or so. No, looks like it's coming about like this. Right, so it's coming out like that. All right. So the idea being that because this critical angle at the back of the raindrop or the droplet is large enough, or really small enough, such that the incident angle is larger, and therefore it internally reflects. It actually reflects it backwards. It's acting like a mirror here, and therefore that's why you see a rainbow when the sun is at your back, because you have to be here. This is your eye, and this is the sun, right? You have to have the sun at your back looking away from the sun. Whenever there's a rainstorm, you go find where the sun is and look the other way, right? Because the light is going into the droplets, reflecting and coming back out, and that's where it breaks into colors. The reason it breaks into colors is due to a couple of things. One being that the index actually depends on the wavelength of the light, or should I say the frequency. And also because there's only one particular drop that will reflect and refract one particular color. So you actually see the rainbow colors due to droplets at individual altitudes. So you see the red because you see all the droplets up there, and then you see the yellows because of all the droplets there, and you see all the blues because of all the droplets here. And also, no one else sees the rainbow you see, which is kind of a fun thing to think about, right? Because you're seeing only this light, and then someone over here is going to be seeing different light from different droplets. So, anyways, bit of funsies. All right, what we want to do now is think about how do we take light from something and use it to focus or defocus beams.
Okay. Now, I want to use refraction to take light and change its path so that we can get the light either coming to a focal point or appearing as if it had come from a focal point. Now, to start off today, since we are probably in the almost closing stages here, what I'm going to do is I'm going to introduce lenses, and I'm going to tell you the major assumption is that we are thinking of a thin lens, such that if we're thinking that refraction that happens is happening basically in one plane, right? We're going to assume thinness. That is to say that the lens thickness is fairly small compared to the focal length of the lens, right? So if you have a lens with a 20 centimeter focal length, you might have a lens that's only a half centimeter thick, right? So that would be thin enough. If we assume thin lenses, we have two types. We have the converging and the diverging. If I want to draw these things out for you, the converging lens would look like that. The diverging lens would look like this. Which is to say, it's like if I took this and stuffed it into there, it's like it's like you take a block of stuff and you carve out this, and what's left over you glue that together and you make the other one. Okay. Now, drawing the ray diagrams for these is exactly the same as drawing a ray diagram for the corresponding mirror types. Okay, we spent some time going through converging mirrors and diverging mirrors, and now we're looking at converging lenses and diverging lenses. Exactly the same situation. Okay, so a converging lens ray diagram would look like this. Okay, I'm going to have a focal point over here due to this surface. I'm going to have a focal point over here due to this surface. Okay, so now I've got two focals, focal number 1 and focal number 2, and because they are located in the same medium, they have the same distance. Okay, I put my object here, and I can start thinking about what rays should I draw. Well, in the mirror case, we had the luxury of the center ray, but I'm going to nix that one for these. It's not going to be useful for us. So we have the remaining three. Number 1 is the one that comes in parallel and goes down through a focal point. So let's draw that one. Looks like this. Comes in parallel. Now I'm going to draw to the middle of the lens and assume all the bending of the refraction happens at that point. and it goes down through the focal point that way.
Okay. Now, this is a transparent lens, so its function is to pass light through. This is not a mirror, so I shouldn't be reflecting anything off from these diagrams. The second one would be the one in which I could go straight through, or actually the second one should be I can go straight through the focal point on this side and come out parallel. So I can go straight through the focal point here and come out parallel. And lo and behold, I've got a crossing right here, so my image will be there. Right? The third ray is the one that goes straight through the very middle of the lens and continues undeflected, and you can see how the approximation of thinness comes in here, because we're assuming no displacement of the beam that's significant, right? So the third one would go something like this. At least as far as it's a little wavy, but as far as I can go. These are the three beams that you can use in a lens situation. As we're just coming up on time here, let's take a look at the image characteristics and let's answer the 4 questions for this image. Now, I'm going to ask number 1, is this a real image? And I hope you would say yes, this is a real image. Light is actually converging to that point and then diverging away, so that if we had an eye over here, we could see these diverging beams and we would trace them back to right here, and we would say, oh look, they're images, so as if light's coming from right there. Well, light is coming from right there, so it's an image right there. This is a real image. Where is it located? In this case, it's located behind the lens, but that's okay because that's where we expect it. It's on the opposite side of the object, say behind. We can see it's inverted. And I think it looks like it's magnified. If I'm looking at this picture, it looks to be magnified. So notice that all of the traits of the converging mirror, I could get exactly one of these images from a converging mirror. This is why we like this converging mirror, converging lens. They do the same things, okay? And so when I look at answering the 4 questions for the image, I'm going to come up with the same set of answers with a single lens as I had with the single mirror. I will come up with the same set of answers to the 4 questions. It's just that the image is slightly different. The ray diagram is slightly different, but the quality of the image is exactly the same. Okay, it looks like we're going to have to do the rest of the ray diagrams tomorrow, and we will also pick up tomorrow with then taking the mirrors and lenses and looking at them in combination with each other, and start looking at optical instruments like microscopes and telescopes. So, going from this point, I will say have a great rest of your day, folks, and I will check in with you tomorrow where we will continue our discussion of lenses. Have a great rest of your day.